The recording should be kicking in any moment now. Okay, all right, I've got feedback that there's recording. All right, I'll switch between the chat and this every now and again so that I can see if you have any questions. So if you have questions, please ask them in the chat. So first things first, what's our goal for today? So our goal for today is twofold. From a sort of theoretical point of view and building your understanding of creating data structures, we want to stop just creating programs where the data and the functionality are two very separate things, where we've got a bunch of functions over here and we've got some data over there, and they're not sort of linked together in any way. We would like to try and create a construct that combines data along with the behaviors that are legal on that data. So think about maybe if you've got an array of numbers, those numbers could represent temperatures, they could represent prices, they could represent student marks, they could represent a whole bunch of things. And if you send an array of integers into a function whose job it is to calculate student pass or fail results, and instead you send an array of temperatures, it's not going to know that these numbers represent temperatures. It's going to think, oh, these are just student marks. And let's say if they're in Celsius, maybe they're not very good marks, and we return a failure. And the system's not going to know that a mistake happened because an array of integers is just an array of integers. So wouldn't it be nice if we could group the behaviors that are allowed on a, let's say, a student, together with all the data that defines a student into a single entity, which combines those things together. Or same with the temperatures. If we combine the temperature values along with all of the functions that relate to temperatures and unify them into a single data structure, so that it's not really possible to send the information to the wrong function, because instead of sending an array to a function, you're simply telling a student calculate pass failure, or you're telling a temperature sensor to give temperature readings, or a weather system to predict tomorrow's temperature or something like that. So everything is all unified and consolidated into a single type. So that principle, and we'll discuss that in the theory, but that principle is called encapsulation, combining the data and the operations that are legal on those data into one new single entity. And what we're going to try and do is we're going to try and do it using only the stuff that exists in the C programming language first. And it's going to kind of work, but it's going to be very messy and awkward, right? So it's not the way that it's typically done in modern programming. There are still some important systems that do it this way. For example, the Linux kernel, the heart of the Linux operating system, is written in what they call an object-oriented C style. But C itself doesn't support these principles that we'll learn about from the discipline of object orientation, like encapsulation, properly. And you'll see why when we do it. So we're going to use structs, which, if you remember, were optional this year in Computer Science 1A, but were worth bonus marks. Now they're not worth bonus marks anymore. They're just something we use. Along with memory addresses that store the locations of functions and try and join everything together into one single entity. And then the goal that we're going to try and achieve, or the program we're going to write, is we're going to write a program that produces an image, not just not a picture in ASCII on the terminal like we've done before. We're going to draw a circle, but a proper image with color in an image file that you can work with. So those are the new things we'll take a look at. I see there might be some activity on the chat. Let me just check. Okay, if you can't hear anything but other people can, that's normally a sign then that the problem is on your side. So other people have indicated that they can hear. So if you're unable to sort out your audio problems, it will be hosted on YouTube and you can watch it later. So don't panic, and there will be other copies of the tutorial during the week as well if you want to watch a live one. Right, so let's begin. We're going to make use of the things that we did before. So for example, we're going to make use of libraries in order to do that, to create our image type in a we'll call them pseudo-object oriented style, because object orientation is the thing that makes C++ different from the C programming language. Originally, C was called C with classes because it added object orientation. That was the big thing that made it different and made it a different language when it's evolved. So you'll see what it means to try and do object-oriented programming in C and why it's not that great. All right, so let's do a I'll call it pseudo. Actually, let's just name the file so it's easier to identify on Eve. So it'll be tutorial 2021-0720. But in the inside, we'll name our files such that they're easy to identify. So we're going to, in the same way in the first semester, we did a whole bunch of variations on the same theme, and typically a turn-based game. In the second semester, we're going to do a lot of things that will involve processing and generating and working with images. So the image will sort of be the thing we do most often in practicals and tutorials and in your second semester test and so on, so that you're not surprised by a completely different problem domain when you get to the test. So this is going to be a pseudo-object style image. So I'm going to give it a name, pseudo-object. In the theory classes, we'll discuss what do I mean by the term object versus the term class versus all the various terminology things you'll hear about more as the theory progresses. But we'll call this a pseudo-object or a pseudo-class as we go along. I mean, strictly speaking, this would be the pseudo-class, but not a pseudo-object. So let's even name it that way correctly. Pseudo-class image. Oops, and let's create it in the tutorial directory. All right, so like a normal library, we're going to have a header file. I normally name mine without the included, but it doesn't really matter. Remember the guard conditions to protect it. Now, basically the idea here is we're going to have a separate header file and CPP file to represent every kind of entity, every kind of thing that exists in our problem domain. In this case, we just have the one. It's a class. It's an image. But if you had a problem which involved students who wrote tests and submitted practicals, you would have a practical.h file and a practical.cpp file to represent all practicals, a student.h and a student.cpp file to represent all students, and a class for like let's call it a lecture.h and a lecture.cpp file to represent all lectures and so on. So we'll try and group things based on the kind of thing. In this case, there's only the image, so it's not such a big deal. Is CSC more theory? So yeah, no, okay. So if you've done Informatics 1B, it's the same theory basically, except there'll be some differences because it. Sorry, the question, just by the way, I suppose you can see it, is the difference between Informatics 1B and Computer Science 1B. They're actually very, very similar. So if you're doing the extended degree and you did informatics last year, the theory is basically the same, with only differences that relate to C++. So there'll be some things we do in C++ that you won't do in informatics, but the basic ideas will be the same. So it will help if you've done Informatics 1B, but it's obviously not a requirement. In terms of memorizing theory and stuff like that, so the first test is a theory test, but remember it'll be a sort of an applied theory test. I'll upload past papers for all the semester tests and exams to Eve so you can take a look. And then also the second test. Excuse me, the second test is a practical test, just like in Computer Science 1A and just like in informatics as well. So you'll write a program. The program will almost certainly relate around image processing in some way. As I said, we'll start from the beginning, so it seems familiar. And the exam is theory-based, but again, let's try and make it apply. So is Computer Science 1B difficult? It is more difficult than Computer Science 1A. Remember, in Computer Science 1A, there's a lot of repetition. Here, you learn new things right up until just before the end. So remember, 1A is sort of more like a bridging course for people who didn't program in high school or anything like that, to bring them up to speed. 1B is more like a normal university course. So it is harder. You'll have to work consistently, do your own practicals, and work hard. It's definitely not as easy as 1A. The pass rates are normally lower, definitely. All right, so what are we going to do? We're going to define things that represent an image. So what is an image in any case in a computer? So an image is a whole bunch, if you look at the screen, of points, and each point has a color, right? We call these points picture elements or pixels. So we need something that will represent a color. So how is color represented on a modern screen? Well, color is just light, right? It's light of a particular frequency. So how can we represent the frequency of light? Well, I mean, theoretically, you could have a whole bunch of individual little light emitters in the screen that you could set the frequency exactly, and they would emit the frequency of whatever light you wanted. But that's actually hard to do. So the way color works typically is we only emit varying intensities of 3 colors, red, green, and blue, because those are the primary colors in light. Light is an additive color system. So you can simulate all the other kinds of lights that the eye, all the other kinds of colors that the eye can experience just by varying the amount of red, green, and blue light that you send out. So we call that an RGB color space, red, green, blue. So technically speaking, the yellow that you see here isn't real yellow. It's simply a combination of red, green, and blue that's stimulating the cells in your retina, the part of your eye that receives light, in the same way as actual yellow light would have stimulated your eye. So bear that in mind. The white here isn't actual white light. It's simply maximum intensity, red, green, and blue. And any black that you see isn't actually black. It's simply zero. Well, I mean, that's philosophical, but it's zero intensity, red, green, and blue. So we need something that can represent one point in the picture, one pixel, one color, and it must be made up of red, green, and blue. And typically what we do is we represent those as intensities ranging from 0 to 255. Because if you do that, you have combinatorics, a combination of those 0 to 255 values 3 times, so you can represent millions of possible colors. So it's typically enough for human beings because our eyes aren't sensitive. Most people's eyes aren't sensitive to distinguish between more than a few millions of colors. So we're going to combine them into a structure. So remember, a structure is a container for other data types. So it's basically, think of it like a box that you put the other data in. And we're going to call this, let's say, color. I'm going to spell it the way we spell it. If you're a programmer, you'll see a lot of American style spelling for color because most libraries and things are American, but I will name it the South African English way. And inside here is where you will define your color components for red, green, and blue. Okay, we could put in a namespace if you want. Let's do it just for revision's sake. Let's put it in a namespace. There's no harm. When we do proper object-oriented proper object-oriented programming, you'll see that the need for namespaces is much less because proper object orientation creates its own namespace for every type you define. But it's a good point. No harm. Let's do an extra. Namespace. Right, so we've got our header file for this. Let's create our CPP file. Same name as the header file, except ending in .cpp. And then let's link it to the header file. Since we're using the namespace, let's carry on with that. Color space. All right, great. All right, and then also in main, I guess now we will need to do those two things as well. So let's do it. Let's bring in our library. Separates the system libraries from our libraries, and let's use our namespace. Okay, perfect. All right, so we need 3 color components inside the header file. We need the red, which will make an integer, so let's call it int red, and green, and blue. The recordings for tutorials and for classes will all be hosted on Eve under notices. So there'll be one notice that will keep growing, which will have the red, green and blue, which will have the links to all of the tutorials. Why are the colors integers? Well, we need numbers between 0 and 255. We could make them shorts if you really wanted to be very specific, because we don't actually need all of the integers, and we could make them unsigned ints because you don't want them to be negative. So that's also a possibility. I'm keeping it simple because I don't want to get too buried in complicated numerical types. So we're just going to stick to, it's not going to be a fractional component. It can be, we'll use an integer to represent it. For what it's worth, it is totally possible to represent color with real numbers. And then you would just typically use numbers between 0 and 1 to represent how much red, green and blue there are. So 0 will be no red, let's say for the red components, and 1.0 will be full intensity red. So it is possible to do it that way. We'll stick with integers because, as you'll see, the output format that we're going to use to represent our image expects them as integers, so then we don't have to do any conversions. So that makes our lives easier. All right, so let's so we've defined a color, but we don't just want a color, we want an image as well. So we're going to create another structure, which we will call, let's call it UJ image. It's going to store a two-dimensional array of these pixels, of these color points, so that we can have an image, because that's all an image is a two-dimensional arrangement of little points of color, of little dots. So how would we represent a two-dimensional array of these colors? Well, we would use a color array. So a two-dimensional color array would be color pointer pointer. Let's call it ARY pixels. If you wanted to, we could do type diffs to have a color row. So let's say color pointer, and let's just call it image row. And then this could be a one-dimensional array of color pointers, or if you really wanted, you could keep going. Type def row pointer, and then we could call that image array, and then we could make that simply image array. So let's just comment as we go. So this is a structure for each pixel. Types for array of pixels, for 2D array of pixels, and this is the image pseudo class. All right, so why is it going to be a pseudo class for what it's worth? Well, we'll discuss that in a moment, but for now we've got the array itself, but what we need is we need to store the number of rows as well as number of columns, and so that's pretty good. And then basically we just need the functionality that we would associate with an image. So we're going to keep it really simple here. I'm going to have one for let's say clearing the image, and I'm going to have one for drawing a circle on the image, and one for converting the image into an image representation. So for what it's worth, the image representation, the file format we're going to use, is called PPM. It stands for Portable Pixel Map. And it's very simple. We'll discuss it as we generate it. But just so you know why I'm going to name the functionality to PPM. PPM is the name of the format we're going to use. Incorrect. So the goal is to draw a circle, right, on an image, and you have to basically shape up. You have to deal with it. I understand it's difficult, but we can't wait until we've covered all the theory before starting with the stuff. So the goal is to draw an image. I've stated that already. An image is made up of a two-dimensional array of points, and each point is represented as red, green, and blue colors, which are numbers between 0 and 255. So to be honest, there's no theory at this point in time that you need, because we haven't actually done anything that wasn't covered in Computer Science 1A. So if you are struggling with that, then please review what we did in Computer Science 1A. If you want to take a look at structures in usage, remember we did that in the game framework in 1A. If you're coming from somewhere else, then you'll have to make up the difference. But basically, none of this that we've covered so far is outside of the scope of Computer Science 1A at all. There is nothing that you haven't seen before. All right. Is array pixels a 2D array? Yes, it is, as stated in the comment I just wrote. So you can see we've got a one-dimensional array of records, and then a one-dimensional array of those rows, which makes overall a two-dimensional array indexed by rows and columns. All right, so in order to store the functionality, not just as a separate bunch of functions like we would have done in 1A, but we want to store it inside the structure itself. That's what we call encapsulation. So how could we do that? How can you store functions inside a structure? How do we store functions in anything? Well, remember we discussed in 1A this notion of something called a pointer. And a pointer is simply a place in memory where you can find something. So all of our stuff, when we compile our program and run it, is actually sitting in memory somewhere, including all of the functions. Right? We did discuss this when we did the basic theory of functions, although you didn't need it for the second semester test, is that functions are turned into basically numbers, and those numbers are stored in memory somewhere. Those numbers are the instructions required to execute those functions. So somewhere in memory our functions exist. So what we're going to do is we're going to create a variable that can store the memory location of each of those functions. So we're just going to keep it simple. As I said, let's actually just really keep it simple. I'm going to have a draw image and a convert image functionality, nothing else. So draw circle and convert to ppm. So what would it look like if we were doing a regular function, right? And this is something that'll work in C++, but won't work in normal C. So if I just wanted to put a regular function inside a structure, I could do something like draw circle, right? That would, whoopsie, that would work fine in C++, but we're trying to stick to only the stuff that existed in C to sort of make a point as to why C++ needed to exist. So this won't work in regular C. So what we need to do is we need to convert this regular function prototype into a function pointer. So how do we do that? Well, we take the name of the function and we wrap it in parentheses and we add the pointer asterisk in front of it. This is now no longer a function called draw circle. It is now a variable called draw circle, which can store a void function. The only problem is this function pointer, as it is called, function pointer for drawing a circle, is not actually linked to the structure in any way. It's inside the structure, but it doesn't know about the structure itself. So we have to keep them linked to each other. So the way in which we do that is we're going to need to add a parameter to it, which keeps it tied to the structure it's inside, and we're going to call this self. As you will see when we get to how C++ actually does this, there is a special variable in these data types called this, which always refers to the current entity, the current object as it's called. Exact term doesn't matter. But we're trying to do this using C++, using C style stuff. So we're going to make our own this, which we've called self. So as you'll see, if you ever type the word this, you'll see it's actually a pointer. That's not a pointer, a keyword. So we can't call it the same thing, but it's serving the same purpose. The idea for this is that when you encounter this in C++ and when you see it being used in the theory, you'll actually know what's going on under the hood, because we're building the stuff that we will use in C++ from scratch. You'll see that it's awkward, but now you'll at least understand why it exists. And we'll do another one for converting to ppm format. Right, so for that, we'll want the format back. Let's take a look. I think a question. We need to get that information back. So what is our file actually going to be at the end of the day? It's simply going to be a text file, and we're not going to worry yet about creating the file with the file handling libraries in C++. Those we'll get to later. We're just going to use stuff from Computer Science 1A, where we redirect the output from our program into a file. But this file will be a text file, so in order for that to work, we need to make use of strings. And strings are in the standard namespace. So we can either go using namespace standard, or because this is a header file, it's often common to fully qualify the name instead and say standard string. It doesn't really make a big difference. So here we're going to create this thing and we're going to call it 2ppm. And it also is going to have a UJ image pointer linking it to itself. Join the two together. And that's all we're going to need in terms of the functionality that's stored inside the UJ image. Typically, what we would also like is we would also like the ability to create a new one of these things and destroy one of these things. And we'd really like to be able to bury those inside the image as well, but we can't, unfortunately, using this approach. So those two will have to be separate functions, the creation and destruction function. So I'm going to call one that makes a UJ image. I'll call it make image, and it's going to simply have a number of rows and a number of columns. Likewise, we need a destruction function, which I will call free image, which is going to take in the image it's going to free as a pointer. It needs to set it to null, so a pointer reference, and we're going to call that obj image. And that's what we need. Okay, now maybe is this something for us, or is this? Why did I put standard? Okay, so as I said, remember we have choice here. We can do the string's name is standard string. It lives in the standard namespace. We've got two choices. We can go using namespace standard, right? Which would work fine, or we can go standard : string to give it its full name, because that is the string is inside the standard namespace, just like our color is inside the color space. Now, typically in a header file, it's not considered good practice to use the standard namespace, because lots of people might use your header file and not all of them want to use the standard namespace. So a way in which you can make this work without going using namespace standard is to simply go standard and then the scope resolution operator to give the fully qualified name of the string type. Okay, it's a good question. Why are the function pointers included in the struct? So that's a great question as well. This is our goal in life. We're trying to join everything together into a single new data type. So the idea is that behavior functions and the data that's legal on those functions aren't just separate. They're unified into a new data type. So that's our goal. We're trying to do that using just the tools that are available in C. And the only way we can store functionality inside a structure in regular C is by storing it as a function pointer. So that's the reason why we did it. So that's a good question. You won't be using this technique much. It's simply there to give you an understanding about how C++ actually automatically does the things that it does for you, so that you understand in a deeper sense how it works, not just, use it. Right, so inside our inside our library, we're going to have those two creation functions, creating and freeing the array. We're going to make use of null pointer if nothing else. So I'm just going to turn on modern C++, but it's not really that important. And then we've just got function pointers here. Function pointer isn't a function. It's a variable that can store the place in memory where a function is. In the same way that an integer pointer isn't an integer, it's a variable that can store the place in memory where an integer will be. So we're going to actually need implementations for these two functions, but we're going to keep them private, keep them hidden inside the implementation file, and you can only call them through the image itself by calling draw circle and 2ppm. So I'm going to give them very similar names that it's clear what their jobs are, but this one is going to be called draw circle implementation. And it's going to have the same signature because it's going to be compatible with the pointer. It's going to actually be stored inside. It's going to be stored inside the function pointer. And likewise, in order to get the 2ppm function working, we're going to need a 2ppm implementation function. Okay, here, because this is a CPP file, it's fine to just go string and go using namespace standard if you prefer. That's fine. And it's not a function pointer here. This is the actual implementation of the function. So 2ppm implementation. Okay, that's where the actual logic for those two functions are going to be. Or for those two function pointers are going to be. So let's start off with the basics. Let's start off with creating the image and freeing the image. So for that to work, we're going to need to store the rows and columns somewhere. So let's do that. So first things first is we're going to need to make a place to store them. So let's make a uj image pointer, because that's what we're returning, and we'll call it obj image. And it needs to be allocated some place in memory on the free store, because we're working with pointers here. So we're going to say new, what's this, that image pseudo object? What did I call it? I called it a uj image. Okay, new, oh yeah, there it is, uj image. Right, so that just makes it. Nothing is initialized. Everything is random. We still need to set it up. So we're going to return it at the end of the day. Then we need to store the rows and columns. Obviously, we could add some error handling. I'll leave that as an exercise to the reader to check that rows and columns are in reasonable range and so on and so forth. So let me just make a note here that this is to allocate space on the free store for an image. Now we need to store the rows and columns. Rows and columns in image. So that's going to be, now think about this. This is not a UJ image. It's a UJ image pointer. So first things first, how do we get things into and get things out of regular structures? If you didn't do the bonus marks and you ignored that in Computer Science 1A, you might have forgotten. But the basic idea is with the structure, you use the dot operator to reach inside it and change its value. So let's say you had a student called S and it had a student number called int number. You'd say s.int number equals whatever to reach inside the student S to get its number. We can't do that quite here because what we've got here is not a regular image. It's an image pointer. So we could do two things. We could firstly go obj image, dereference it, and then go dot int rows equals, and then the parameter int rows. That's fine, it works. If you agree this is ugly and messy and it looks more complicated than it needs to be. So I'm going to just leave that there for educational purposes and say using dereferencing. And now I'll do the columns the other way. So we're going to say store. So I'm going to do two comments. Let's say there. Columns using the special operator that combines those two together. So reaching into a pointer to an object, dereferencing the object first and then reaching into it is so common that they've made up a special operator to do it. So instead of going star whatever my structure pointer is dot, I can just go my structure pointer arrow int cols is equal to. That's much. It's a combination of the dereference star and the member access dot. So it's just a convenience, but you'll see it used a lot in practice. So now we've got our image, but it's just got rows and columns. It doesn't actually have the inner array created in any way. So that's our job now, just like we would do in the game. We need to make the array. So we need to go create the outer level of the array. So that's ARY pixels, and that's going to be an array of color pointers. And it's going to be as big as the number of rows. That's just the outer level of the array, so we need to loop over every single row and create the inner row array, which is as big as the number of columns, and we need to set it to something. So what would a blank image look like to you? And I would agree that a blank image could either be a pure white image, like it's a page, an empty page. So if you open up Paint, for example, I think its default color for a blank image, of whatever size, it's a very small one, but you can see that it's white. Or it could be a completely black image. And those kind of make sense because that's maximum intensity or minimum intensity for all the color components. So pick one. I'm going to go with white like in Paint, but you could make a black image as your default as well. That would be just fine as well. But either way, we need to do this for every single row. Actually create the inner row array. So obj image, reach inside the pixels array at position R to create the new actual array of color components. And it's as big as the number of columns. Okay, see there's another question coming through. Let's just ask. What is obj image in this case? Okay, obj image is created over here, and it's simply one of these structures. So basically, it's a array of colors. And what's a color? Red, green, and blue. A two-dimensional array of colors with size, row, and column, as well as the pointers to the two functions for drawing and converting into our text format. That's all it is. It's a bundle that contains some data. The data is in the form of the size and in the form of the colors, which is a 2D array of structures, and as well as some behavior. And the behavior is in the form of a drawing function pointer and a conversion function pointer. So that's what obj image is. So at the moment we're busy creating our image structure by creating first the size, which we did, and now actually creating the array itself, and then setting each of the points inside the array to a starting color, which I'm going to say white makes a pretty good starting color for that, or black. Right? So those would be the two possibilities. So anyway, here we've created the inner row array, which is as big as the number of columns. Now we can loop over those columns. And we can set them to something. So we need to set each pixel. So we need to reach inside the image to get the array of pixels at position row and position column. But remember, this isn't a single value, right? It's actually a color, and a color is 3 values, red, green, and blue together. So we've got 2 ways in which we can do this. We can reach into each of those and then go int red, int green, and blue, and set each of them to their value one at a time, but you can see that gets a bit messy. Or we can set up this current pixel first by making a color record. Right. Set it up first, dot red. Okay, so let's go for a white image. That's 255 for everything. excuse the typo, as well as recpixel.blue. So red, green, and blue are all 255. And then at the end of the day, what we can do here is we can say is equal to recpixel, because then it will copy the whole pixel red, green, and blue all together into the array of pixels at that position. So once these loops are finished, we will have a two-dimensional array of pixels, and every pixel will be white. So it'll be a single blank image. So in terms of the data, we've set everything up. So we've handled this so far. But remember, inside our image, we also had some behavior, the behavior for drawing and the behavior for conversion. So in order to store those, we need to actually set those two pointers to be equal to those things. So we don't have the behavior yet, but we have created the skeletons of those two functions, so we can set them up in the meantime. And what we need to do is we need to go, before we return obj image, we need to set the draw circle pointer to be equal to the place in memory where the draw circle implementation function will be. So just hang on, I've got a question, so let me just answer that. So do you want it to be black? Exactly, perfectly, 100% correct. If you wanted it to be black, you'd set them to 0, and anything else can give you all the other colors you want. So if you look inside, like if you can search for the red, green, blue values for any color that your screen can represent. It's called the RGB code. So that's right, and black is 0 and white is, so if you want, okay, for what it's worth, an easy one, if you wanted to make the image start off as just pure red, then you would set red to 255 and green and blue equal to 0, and that would give you just a plain red image. So very good point there. Okay, so what have I done here? I've said, give me the place in memory, the address of operator. Remember that from when we did pointers in 1A. So this will take the address of the draw circle implementation function. Now, technically speaking, this ampersand isn't necessary because a function name in C and C++ is always the place in memory where that function is. So you could leave that ampersand off, but I always leave it there just to remind myself when I read the code that I'm definitely talking about a memory location. So we've got the draw functionality set, and now we're going to set the conversion functionality. The functions don't do anything yet, but at least the memory addresses will be valid. I'm not calling the function. Notice I don't do that. I'm not actually calling the function. I'm simply taking the place in memory where the function is and storing it inside the image. So now we've got an image that's properly set up, except for the fact that these functions don't do anything. The array is set up. It's a blank white image, and the pointers are now valid, even though the functions are empty. So this is a correctly set up pseudo object, a correctly set up entity. We can return it and do stuff with it. What stuff would we do? We would call the two functions, and that's basically it. And before we're done here, let's just also discuss getting rid of our array, and not just our array, our image. First things first is we need to loop through all of the rows. Now I can't just go int rows here because int rows doesn't exist inside this function. So I need to reach inside my image and get the number of rows that it has, which is going to be inside it with the arrow operator for every row. And then likewise, we need to delete that one row array at a time. Then when we're done, we delete the outer array. So you can see this is exactly the same process as we followed with the 2D games. That's why we do those two different things in first and second semester. They're similar but different. And now we can delete the outer array as well. And then I suppose if we really wanted to, we could set the image equal to null. So we've got the creation and destruction functionality. What we don't have yet is the actual drawing of the circle or the conversion to a visible representation. So before I do the drawing of the circle, let's actually get to the point where we can test that this at least kind of works, and let's generate our text representation of the image so that we can output it to a file, so that we can open the file and see if this works. So if you want to, okay, so there's another question. Let me just check. Yeah, so you can think of that arrow operator. That's perfect. You've 100% correctly got it. The arrow operator, if you've got a pointer to a structure, that's how you get things inside it. So let me just summarize that. So pointer to struct, use arrow, regular struct, use dot. It's exactly the same function as dot, except it also dereferences, so it makes your life easier. So that was a very good question, thank you. All right, so let's begin. So first things first is we're going to make our string that's going to represent our text version of the image. I'll call it strppm. ppm, remember, stands for portable pixel map. So create string for portable pixel map, and then at the end of the day we're going to return that string. So what does the ppm format look like? Okay, we'll do so many examples with it, you'll be very used to it, but it's just a text file, and it's a text file with a certain structure. The first line in the text file tells us whether this is a color image, whether it's a grayscale image, or whether it's a black and white image. So the first one tells us the kind of pixel map that it is. So P1 is a black and white image, P2 is a grayscale image, and P3 is a color image. So we're telling it, okay, we want a color image. And then we want an end of line function, end of line character, so that's \n. The next line tells us how big the image is, and it starts off with columns and then has rows. So we could also do this if you don't want to muck about like that. Let's do it with a string stream, because that's how we did a lot of work with string streams for conversions before. So let's just do it again. Hash include string stream. So let's do it. String stream ssppm, and then just try and remember what the conversion function is. So it's ssppm dot str, I think, yeah, to convert it to a string. Yeah, so there we go. So we'll work with the string stream so it looks more similar to our number conversion functions from the first semester. So first thing we want to do with the string stream is we want to put in the P3 to represent the end of the line, to represent the fact that it's a color image, followed by an end of line. Then what we want to put in is we want to put in the size of the image, but the format says it wants columns first, then rows, so that's fine. So we'll just do it like that, ssppm, and we'll go obj self. So remember, the image is coming through as a parameter called obj self. Obj self, arrow int calls, and then a space followed by the rows. And that's that. Then the third line in these images is always the maximum value that any component can have. So for example, if you're doing just a black and white image, you can just represent it as zeros and ones, zeros for black, ones for pure white. So then your maximum intensity would be 1. If you're doing grayscale, you don't need that many shades of gray, so you can pick anything you want, 10 or something. But if you're doing a color image, your maximum value for each color component or each image component should be 255. Okay, so that's the header, the first part of the file that sets up the dimensions of it. The rest of the file is simply made up of each of the pixels, each of the color points, red value, space green value, space blue value. And if you want to, you can format them so that each row in the text file represents one row of color in the image. But you don't have to, but it is easier then to read the file as a human, but it's not required. We will do it that way just because it's not difficult to do. So here we will have to loop over every row. Remember, we need to get our image from inside the structure for every column. We need to represent the column component, reaching for the column component. Now here we have both rows and columns, and we can reach into the array and get out the red value, green value, and blue value. In the same way that I did it for initializing, make our lives easier rather than mucking about with a long thing each time. Let's just make a local color for that pixel. Grab it from the array of pixels. Now we can just work with rec pixel for our output. So into the ppm, we're going to put rec pixel dot red and a space, followed by rec pixel dot blue, sorry, green and a space, followed by rec pixel dot red, green, and blue, and a space. And then at the end of each row, just for making our lives easier, if you need to look at the file, we'll put in an end of line, but it's not really necessary. And technically, this is all we need. This will generate a string version of our image that we can then open as a file with the right programs. Now, the programs aren't complicated. Unfortunately, Paint can't do it, but many other image viewing programs can. And if you've used, for example, OpenOffice, that can handle it fine, or there are other tools for viewing them, which I guess I can mention when we get there. So let's first just create such a thing. So I'm just going to do it hard-coded. We're not going to worry too much about handling command line arguments or anything like that. But what we want to do is we want to make ourselves an image. So uj image, make image. Let's do 800 by 600. This is just going to be a pure blank image. We want to output it, so we're going to output obj image. Now we have to call the behavior. This is where it gets a little weird, and this is where the sort of limitations of using just C-style programming techniques to create these unified encapsulated entities breaks down. So we want to call the function. Ideally, we'd love to call the function just like this. We're calling inside that image, we want to call draw circle, but it doesn't work that way because this draw circle doesn't know where it is, and it needs to be linked back to the thing that contains it. So unfortunately, and this looks terrible, we have to pass it to itself as well, which really is a bit weird, but that is the limitation of this technique. Then when we're done, we can call free image and deallocate that. I see a question has come through, so I'm just going to answer it. Let's take a look. It's not a built-in function. We just wrote it, remember? If you look inside the header file, over here is make image. We defined it in the header file over there, and that was the function we wrote over here, make image, where we create the image, store the rows and columns, create the array, set everything to white, store that inside the array, capture the memory addresses of the implementation functions, and return it. So we created make image. It's not built in. We just wrote it right now. Same with free image. That's the one we created over here, where we loop through the array, delete each of the row arrays. So we loop through the outer array, delete each row array, and then delete the outer array and set it to null. I suppose what we could also do, just to make sure no one accidentally uses this afterwards, is we can set the rows and columns as well equal to 0, because it's an empty image, as it were. So that's what's going on in this behavior over here. We're making and destroying, and here we are converting and drawing a circle. We haven't done the circle drawing bit yet, but we'll do that now. The first one to just test if we can actually output the circle. So if we run this now, we should get the stuff coming to the standard output stream, which in this case will be in the terminal, which will appear. But we want to redirect it to a file so we can open the file, but let's just test if this works so far. So let's compile. Oops, looks like we've got an error somewhere along the lines. Ugh, not draw circle. Sorry, I meant 2 ppm. We haven't drawn the circle yet. So I was complaining about that. Okay, perfect. And then let's run it. So you'll just see a bunch of numbers flashing by, but if it doesn't crash, that's a good sign. Yeah, so it's just all the 255s that represent the white pixels. Did get a bit unhappy at the end there. I wonder why. Ah, yes. Okay, well, what's something we can also do here, sorry, in deleting it, in addition to just deleting the yeah, there's actually a couple we can do. We don't need to set these to 0. What we can do, we've deleted the array. After we've deleted the array, we can delete the image itself, and which is not an array, and then set it to null. So that's actually a much better deletion function. And then we shouldn't get that error code at the end afterwards. So let's try again. We should return 0 at the end, which we do. Okay, I see another question has come through. Does the destroy part follow the same concept? It's exactly deallocating memory. So this is no different from first semester stuff. Remember, that's the whole goal of this, is we aren't using any new techniques that we haven't seen before, except we never bothered to take the memory address of a function, but it's, you know, we did show you that you could take the memory address of things. This time we happened to be doing it with a function. We did talk about function pointers, although it wasn't a requirement for the semester test or exam, but those were covered. So the idea is that we're just doing stuff that you already know. And yes, delete is exactly what you saw before. For every new, there must be a delete. So there is a new for each of these row arrays over here. So there must be a delete for each of those row arrays. There's a delete for the outer array, and that means there's a single delete, a new for the outer array, and likewise there's a new for the UJ image, so there must be a delete for the UJ image as well. So it's exactly the same as what you saw before. All right, so we've got the basic thing. Let's test to see if we can run it in from I was doing that on the desktop. Tutorial. Let's run it and then see what happens. So if we run it, you can see that we're going to get, again, just that stuff to the screen. But if we want to redirect it to a file, we can do that, just like we did in the first semester. So let's redirect it to a file. Let's call it image.ppm. And then if you've got the right programs installed, OpenOffice is one. Okay, we won't be able to actually see anything here because it'll be white on white. So let's just change it to black momentarily. So as long as there's no error message, okay, we can't see our white image. Maybe if I can grab it, yeah, you can actually see it is there. But let's just for the sake of visibility change it. So we can change it to a red image. Just so we did that. And regenerated it and opened it. You can see we've now got our red image. So for what it's worth, yeah, OpenOffice will handle it. That's free software. Another piece of software you could use is something called GIMP. We'll post a link to that in any practicals that require you to work with these. All right, so now the only thing left to do is to draw a circle, and we've kind of done circles quite a lot in the first semester with our various practicals and so on, but let's do it again. So if we just want to draw a circle, let's put the circle roughly in the middle, or exactly in the middle, but we need a distance. So a distance function, so it's going to give us back a real value. Let's call it distance. It's not a function that needs to be called from outside the library, so we're not going to put it in the header file. And it's going to give us the distance between a row. Actually, let's do this in a structure-based way, just from some structure practice. Let's have a structure to represent a coordinate on the screen. And so what that's going to be is it's simply going to represent a row value and a column value. And we're not going to make it into a pseudo object or anything. It's just going to be a regular coordinate, but then we can very easily do this. And we can say the distance between two coordinates. So coordinates rec C1 and another coordinate rec C2. Then we can work out the distance between those two coordinates using the Euclidean distance function, which is inside, or the building blocks are inside CMath. So let's bring that up. Remember, the distance between 2 points is the difference between the squares of the corresponding components added together, all square rooted. So basically what we'll want to do is we'll want to return square root of squares. So we're going to use the power function for that. So rec C1s, let's do the rows first. Row minus rec C1 dot row raised to the power 2. And we're going to add that to exactly the same story, but for columns. I think that lines up. Yes, it does. So now we've got our distance function. So in order to draw the circle, all we need to do is we need to loop over every point. And let's just put the circle center in the middle. So over every point in the image, for every row from the image, for every column in the image, okay, then what are we going to do is we're going to calculate the distance. And if the distance between that point is less than or equal to some radius, now we haven't actually, let's add that. I didn't think about it before, but let's just do it. So let's say we've got a radius, or let's make it a double even, for our circle. And then we need to add it to the function pointer as well. So we can draw a circle of various sizes. So if that distance is less than or equal to the radius, it's in the circle, otherwise it isn't. And yeah, that's basically it. So let's get the center points of this image. So let's put that in the coordinates, I guess. Coordinates, rec center. Rec center's row is going to be halfway through the rows. And rec center's column is going to be halfway through the columns. And then we're just going to compare and see if it's halfway to that center point, if it falls within the length of the radius to that center point. All right, so if the distance between, let's do a thing for this point here, so rec Okay, so if the distance between our points, doesn't matter which order you do them, distance is the same in either direction, rec point and the center is less than or equal to the radius, and it's inside the circle, which means we set that point to a color. Let's set it to black, I guess. So rec point, sorry, not rec point, inside the circle. Yeah, well, let's do, color, rec pixel, dot red. Now there are quicker ways of writing these structures, but I want to do it the long way first, so you're used to the whole idea of what's going on. Red, green, and blue. So that's just the black pixel. We could actually let's just call it rec black, so it's clear what its job is in life, is to just be a black point. And then that's going to be the color of our circle. So inside our image, which at the moment is our self, inside the array of pixels at row and column, we've got a black pixel instead. And now our image will be contain a circle with the given radius. So let's add that to our main here. So after we've created the image, but before we convert it to a string, let's draw a circle. So let's make it a couple of hundred pixels wide. So draw a circle on this on itself, and let's make it, let's say 200 pixels wide, and then let's compile. Okay, that seems all right. Let's run it and see if it at least, it looks a little bit like a pure black image. I'm a little concerned. Let's make it a bit smaller. Let's check also. Oh, we set it, no, we didn't set it to black originally. We set it, just check. Let's just set it back to 2555. Let's see. Okay, let's just compile again. And I just see if we have a question, so let's ask. Does the combination of RGB pixels make one color? Yes. So every single point, every single color is made up of a combination of some red, some green, and some blue if you're working with light, which obviously a screen is, because the screen is projecting light at your eyes. So every single point in a color image is actually made up of 3 individual values: red, green, and blue. So that's a very good question. All right, let's see if we now get something that looks a bit more reasonable. That is a lot of, what is going on here? I feel like my logic is a bit messed up. Rebuild. The radius, how big was the radius? Wasn't that big. That's very weird. Let's just compile and run. Okay, so you see there's more. Okay, so you notice, oh, am I subtracting things wrong? Let's check that out. That seems like a good place to look. Aha, thank you. Excellent. Well done. That is brilliant. So I'm supposed to be comparing 2 separate things, not subtracting the thing with itself. Obviously, that's never going to be anything other than 0. Excellent job. Well done. Really well done. Now I should get a mix of stuff. Yep, you can see a brief glimmer there when we hit the other stuff. So perfect. That was exactly the error. You fixed it. And let's transmit. And let's open. And there we have our image with a circle in the center. You can see the outline of the image itself, and you can see the black circle itself. If we opened this up, just remember it is at the end of the day just a text file, so we will still see at the beginning of that text file our P3, that means a color image, the dimensions, maximum value, and then red, green, blue, red, green, blue, red, green, blue for every pixel in the image. And that's basically it. So those were some really good questions and comments. Thank you very much for your participation, and thanks for spotting that error. That was very well done. So that is it. I will stop recording, and I will upload this and the other things that have occurred so far as links to YouTube on Eve, and I'll see you in class later on today. If there aren't any other questions, that's it. I will upload the source code to this as well, and we will upload the videos. So thank you. Will I be? So I mostly want to do this TUT, the one on Tuesday. Sometimes I'll have to do the one on Friday, not Friday, on Monday evening. So I think Mr. Satungu and me will swap between those two. So, well, not swap, but there'll be some weeks when I can't do the evening one, and some weeks when he can't do the evening one. And so we'll alternate between these two. But mostly I think I'll be doing this one. You only need to attend one a week, so it's a good question. We did cover it in class yesterday, but you only need to attend one because they're all repeated. But if you do miss, we do post the links as well online. But we want you to attend one. If let's say you do attend the one on Monday or on Tuesday and you're still confused, you can go to the other ones as well, and maybe having seen it twice or a different approach to it, it will be easier to do it. So you can see, you must see at least one, but you can see all of them if you really want. But it'll be the same content each week in the tutorials. Classes are all different and all compulsory. So very good questions. Thank you. I'm going to stop sharing my screen. I'm going to stop recording now. Thank you for your attendance. The recordings, good questions. So the recordings for all of the classes and all of the tutorials will be uploaded to Eve under notices. So there'll be a notice for the links to past classes and a notice for the links to past recordings. The ones from yesterday, they finished indexing on YouTube, so I should be able to link them now. And these ones, I'll still have to wait for them to the recording to become available, and then I have to upload them to YouTube, and then they have to index on YouTube, and then I can link them. So there might be like a day or so lag between something happening and the link to the video appearing on Eve. But they'll be on Eve under notices. So very good question. Thank you very much. Okay, and let me stop sharing and stop recording. Thank you and goodbye.